Hey everyone, back to a new awesome video, and today we continue with our series about classical mechanics. Today we will finish with angular momentum. First we will relate kinetic energy to this angular momentum. Then we will introduce angular impulse that is similar to impulse but for angular variables. And finally we will revisit this conservation of angular momentum in terms of angular impulse. So let's start. Great. Imagine that we have a rotating object, whatever type, with an angular velocity w. Also, we'll denote this the k hat direction. And then remember from our previous videos that the kinetic energy of rotation, k rotational, equals 1/2 I on the axis of rotation w squared. Moreover, we found on previous videos that the angular momentum L equals I in the axis, as this object is symmetrical, take that into account, times W, the angular velocity. Therefore, we conclude that the magnitude of the angular velocity equals L, the magnitude of the angular momentum, divided by the moment of inertia. Therefore, we can substitute this expression onto our expression of kinetic of a rotational energy, and we find that k rotational equals 1/2 times the moment of inertia times L squared divided by the axis, moment of inertia on the axis squared. Then we can cancel one of these, square with this one, and what we find is that the kinetic energy of rotation, k rod, equals L squared over 2I in the axis. And again, if this object is symmetric, by the same reasoning as we had in the previous video, this quantity is going to be independent of the actual rotational point. Moreover, we find that this is remarkably similar to the expression with linear momentum, in which k equals p squared over 2m. And again, we find these relationships between moment of inertia and mass, normal momentum with angular momentum, and force and torque. Alright, now let's introduce angular impulse. But first of all, let's recall what normal impulse was. Imagine that we have a particle with mass m moving at velocity v and momentum p, and it's here at position with respect to this, it's at position r. And then we have a force being applied to it. Then we know that in the next time interval, in this time unit, the velocity is going to have changed a little bit. Specifically, let's consider the momentum instead of the velocity. We would have a new momentum, p prime, and there will be a change in momentum. This quantity is what we consider the impulse. However, to calculate the actual impulse, because this is just an approximation, we need to do an integral. Therefore, what we do is to, from t0 to t final, integrate the force times time dt prime. And we're going to end up with a quantity which is I, the normal impulse. Similarly, by analogy, we're gonna use this and represent angular impulse. So we would have from t0 to tf, and we're going to integrate the torque over dt. And then this is going to give us, this is equal to the angular impulse. This is going to be our definition. Right, now let's derive from this the conservation of angular momentum. If we substitute in the linear form just to see how this procedure is carried in the linear variables, we have that this is going to be equal to d0 to t of dp dt prime. And therefore, and this would also be prime because it's a dummy variable and we have the integration variable over there. And this, by the first fundamental theorem of calculus, tells us that this is going to be equal to p at t minus p at t naught. Therefore, this is going to be equal to the change in p. Similarly, we have that this is equal to t naught to t of dl dt. And we'll assume that we're in the center of mass reference frame, so that we don't have to take into account the axis of reference. If we weren't and L was to depend on this reference frame, then the angular impulse wouldn't change, because this is a different reference frames alters L by a constant value. Therefore, there will be no problem with not having a center of mass frame. But we will just keep it this way because it makes the math simple. Then we'll have this integrated over dt prime. And this, again, by the first fundamental theorem of calculus, gives L at t minus L at t naught, which is the change in L, in angular momentum. However, we observe that if the force over this interval is zero, the total force that is being applied, this angular momentum is going to be zero. Similarly, and this is the important conclusion that we reach, that if the torque equals zero for t in t prime in t naught to t, then L at TA equals L at TB if TA, TB are inside of T naught, T. So this implies that the angular momentum is equal at every point in this interval if the torque is zero for the entirety of the interval. So that's all for today. I hope that you understood everything and you developed a sense of how angular momentum works and how it relates to all these rotational variables that we have been defining through the last videos. Any doubts left, you may ask them in the comment section and I'll try to answer them in the best way I can. Remember to like the video if it was the case, subscribe to the channel and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome.